Hello everyone. Let's begin today's session with something really simple, yet something we use every day without realizing it. Have you ever tried telling your friend how far your school is? You might say, it's 3 kilometers, but have you noticed? You're actually using a physical quantity. Physical quantities are the things we can measure, like mass, time, temperature, and distance. They help us describe the world in numbers. And guess what? All physical quantities fall into two categories: scalars and vectors. The difference? One just gives the number, the other adds a direction to it. Let's explore what that means. Now let's talk about scalar quantities. These are the simplest kind. Scalars only tell you how much, not which way. For example, if I say the temperature today is 30 degrees Celsius, you know exactly how hot it is, and you don't need to know in which direction the heat is flowing. To fully express a scalar quantity, you only need two things. First, the numerical value, like 30, and second, the unit, like degrees Celsius. Scalars follow the basic arithmetic operations. You can add, subtract, multiply, or divide them without worrying about direction. Common scalar quantities include mass, time, energy, distance, and temperature. For example, mass is written as small m, time as t, and speed as v. Now let's turn things up a notch to vector quantities. Vectors are special because they carry not just magnitude but also direction. Imagine someone says, a train moved 100 meters. You might wonder in which direction? North? East? Without that, the info feels incomplete, right? That's where vectors come in. To define a vector quantity completely, we need three parts: the numerical value, the unit, and most importantly, the direction. Examples include displacement, velocity, force, acceleration, and momentum. To show direction, we use symbols like an arrow over the letter, for example, V with an arrow on top for velocity, A with an arrow for acceleration, and F with an arrow for force. Now, how do we actually work with vectors? Since direction matters, we can't just add them like numbers. We must follow specific rules, like the head-to-tail method or the parallelogram rule for addition. Also, the direction of a vector is shown using an arrow. For instance, F means force in a certain direction, and negative F means the same force, but in the exact opposite direction. Here's an interesting part: multiplying a vector by a scalar only changes its magnitude. The direction remains the same or flips if the scalar is negative. So, vectors aren't just numbers, they're little arrows in space, telling us both how much and where to. Let's cement this with a real example. Imagine a student walks 5 meters to the north. What if they covered? The total path length, 5 meters, is the distance, a scalar quantity. But if we include the direction, 5 meters north, we are now talking about displacement, which is a vector. So, distance equals 5 meters scalar. Displacement equals 5 meters north vector. This is why Google Maps doesn't just need distance. It needs direction to show you where to go. That's vector physics, helping you navigate. Alright, let's wrap up what we've learned today. Scalar quantities are those that require only a magnitude and unit, like speed, time, or mass. Vector quantities, on the other hand, need magnitude, unit, and direction, such as velocity, force, or displacement. Scalars are simple and follow regular arithmetic. Vectors follow a different set of rules, because direction changes everything. From how a football is kicked, to how a drone navigates, scalar and vector quantities are constantly at play in the real world. I hope you now have a clear understanding of how these two types of physical quantities differ and why both are essential in describing the physical world. See you in the next session with another fascinating concept of physics.